to the end, it's just beginning. Life is getting lighter while the days are getting brighter, yeah. And it's a good, I won't even worry anymore. Took all my cares, took and kicked them all out the door.
Welcome to Austin, the DDR capital of the world, I think, right? DDR capital of the world, or something like that. I'm going to talk a little bit today about True Circuits, and I'm also going to talk about a new product that we just announced, the DDR5. And I'll spend most of the time on that. And our booth is right across. So if you don't get your questions answered here, you want more in-depth answers, or you want to get some collateral, we're literally right across the hall. So True Circuits is been an IP company for 15 years. So we're actually one of the pioneers in IP, and certainly one of the pioneers in hard IP. And for the last 15 years, we've been the leader in PLLs, DLLs, timing IP. And we've built an entire automated way of dealing with IP. So we can build IP that fits in a lot of different applications within the chip, but built from one sort of common database. So what we've done here is we've taken, for DDR, we've taken this 15 years of tools of timing IP and taken what we essentially believe is a timing problem, DDR, and we've turned that into a DDR5. So, and we've used the tagline DDR Reborn. And what we've really tried to do is we tried to bring our entire arsenal of IP to the problem, and we've tried to solve more of the total problem. And that's been one of the issues with DDR, because DDR is a wide parallel interface. It many times dominates the I/O and even the economics of a chip. And so we've basically started with a clean sheet of paper. We threw an arsenal of IP and tools, libraries at the problem so that we could solve the whole problem. And so that we could solve the problem for the customer, we could take a lot of the inconveniences of DDR and basically round off the edges. But as much as anything else, it's because DDR has such a huge impact on a chip, on the package, on the die size, on the I/O, on the board. And these are the kind of economics that might be the difference between winning and losing in a really competitive chip business where the gross margins are already razor thin. So what we've tried to do, we've got a picture of the sort of a block diagram. It's probably a little bit more detailed. I'm not going to try to go into it. But we've tried to build something that has a tremendous amount of physical flexibility so that you can bend it around corners. You can build your I/O. You can basically build an I/O ring that fits your situation, that tunes or balances your economics, and then we just build the PHY behind it. So completely assembled, completely validated, and with a small localized interface to the memory controller, which is also de-skewed. So you build this I/O ring, you set your economics, you decide the size, you decide the decoupling, you decide the package, you decide the board, you make the trade-offs you want. In your case, trading some die size for a lower cost package might make a lot of sense. Other times you may have something else. And then we build the PHY, and then the controller closes timing to the PHY very, very easily. We also have a controller partner, Northwest Logic. One of their representatives is over in our booth, so that if you want, we provide a complete DDR solution, controller, PHY, everything, already put together, already optimized, delivered to you, configured and running. We also wanted to fix some of the things about test, because the DFT portion of DDR is pretty tricky. Okay, let's make sure we're not queuing. So we have a full speed read-write BIST. So we use, we loop back a complete write and back into a complete read. In addition, we have all the standard DFT views, the scan chains and the boundary scan. We provide all the views. You don't have to, for things like loopback, it's automatically tuned, so you don't have to have a test engineer, fitzing around trying to get the cycle tuned. So the idea on really everything we do is to make it easy. And integration of IP is still it's still the main problem. The average customer still spends 3 times as much time, effort, and money integrating as they do for the price of the IP. And especially when you have something that affects so many pins, typically is at the very top level of the SoC. It's typically the kind of thing that's done late in the process, where you don't have time, unless you're one of the many chip companies that are always hit things on time, and you always have an extra month before the tape out date. So, you're planning to play golf at the end. And then, of course, the loopback provides pseudo-random data and just makes the whole test process easier. Also, there are many features of the PHY and the memory controller from Northwest Logic that allow you to do a lot of testing at the board level. So, there's the complete memory test package. So, not only can you use it to obviously test the chip in manufacturing 100% ATE test, but you can also use a tremendous number of resources to characterize the PHY that you've built, the package that you built, the I/O ring that you've built, and that's also in there. Seems like I'm going backwards instead of forwards. So obviously we're going to support all the standard JDAC standards, 2400, and we think we're well poised to support 3200 when the specs are released. We've actually designed the entire piece of IP to run at 4 gig. So we have our own libraries and our own tools, and we routinely build PLLs and things like that to run at 3 gigahertz, 4 gigahertz. So we're going to make sure we're as prepared as we can for those next generation standards when they come out. We've also built a bevy of resources. Essentially, we've built this PHY more like a SerDes than a traditional DDR PHY. Every pin has its own timing and logical resources to adjust. So you automatically deskew the DDR PHY, and you essentially solve all of the issues that exist with parallel interfaces. So you basically take a parallel problem and you solve it in many cases like a SerDes. So all the pins automatically deskew, they automatically correct. The tuning is in many cases continuous and automatic. All of the training, VREF external, VREF internal, write training is all automatic. You don't have to write any firmware. Especially if you use the memory controller that we have from Northwest Logic, all that's done automatically. So, software is becoming it is already the long pole in the tent and the most expensive part of building a chip. And so in this way, you're reducing the amount of firmware you have to write, you're reducing the amount of software, you're doing everything automatically. And there are also resources for measuring jitter. There's resources built into the PHY that you can completely map the data I. So when you get your chip out, you're looking at your package, you're looking at your board, you can very quickly get an assessment of every pin. You can find any weak areas. Right there in the lab, you can find a problem in the first couple of days. And that's really important because most of the time when you bring up a chip, until the memory interface is working, you can't boot it up, you can't run all the software. So it tends to be in the critical path of development. So you want to get that DDR interface running as fast as possible so you can do the rest of the chip analysis. And that's the way we've built this in. We've also built features like I talked about that can lower the package and board costs. So we really built this product around the problem. We looked at the entire problem and the economics, and we built a product that would fit that and allow the customer the kind of flexibility that they want. So,
questions for Brian? I have one. And what is the importance of low-powered jitter for PLLs? Why is that important?
So, let me just say low jitter. Jitter. Jitter takes directly out of the budget. So, if you have a data I, you want the data I to be as wide as you can. And if there's jitter on that, it's going to destroy the data I. It's going to take away from the data I. And especially on the clock pin, there's a really tight jitter spec that you have to deal with. So that's especially critical. But just in general with DDR, there's so many if you put together a timing budget, it's a really long list, and you want to try to keep, each one of those elements as low as possible, so, you have a little budget left over at the end.
Any questions? What?
What other controllers did you actually test it with? Like you said, Northwest, right?
Yeah. So the PHY is DFI compliant. So DFI is the official spec between controller and PHY. So the PHY will work with anybody's DFI compliant controller. Now, what we wanted to do was do two things. We wanted to develop with a lead partner, and that's why we picked Northwest Logic. And we wanted to make sure that we had a partner that between us we could deliver a complete solution. So all of the initial work we've done is with Northwest Logic. They also have some really good, a really good memory package option. So if you use their memory test option, then you can completely bring up the interface without having to bring up any other part of the chip. You can just do it a JTAG pin or an I2C pin. You can completely bring up, test, do all the training, completely evaluate it. You can do data eye plots without any instrumentation, without a scope, and we wanted to be able to offer that. We haven't done any certification testing with anybody else yet, but we will.
Another question? What end? I don't know if you already answered this. What are the end products, the products and the applications that your products?
So it really just about any SoC. The DDR. It's almost impossible to build a highly integrated SoC that doesn't have to have external memory. So the IP TAM for DDR has exploded over the last 5 years. Really, 5 years ago, most people did their own DDR PHYs and controllers. And in fact, probably still, most people do their own. Certainly the big companies do. And I think, honestly, it's because it's been hard to have the kind of choices you want. If you're buying a SerDes, you're interested in the size and the power. If it's a little bit bigger than what you hoped, or the power is a little bit more than what you hoped, it probably only has a 0.5% impact on the chip. So, it's not going to be a life or death thing. If you go to a DDR, if you were planning on building a wire bond, product, and suddenly the DDR5 causes you to move to flip chip, that may be the difference in gross margin between wanting to be in the market and not wanting to be in the market. So what that's done is that's forced a lot of companies, especially the larger companies that are heavily measured on gross margin, to have to do their own thing. Because, you just can't, today you can't throw another quarter into the cost of a chip. It's just too competitive in most of the fields. So we've really aimed it at just about everybody. We've tried to build flexibility so it'll run in wire bond. Because we do auto correction, so adjacent pins in a byte lane can be off by plus or minus half of the UI. So you could actually intentionally skew if you really want to try to get the last drop of performance out of, say, a wire bond power delivery system. If you skew adjacent pins, it's a little more work. You have to do more work in the board and to some degree in the package. But that allows a power delivery network to recover between the two switching. So there's a lot of things that can be used. We put a lot of features in that are really sort of power user features, and probably the smaller companies won't bother with them, but some of the bigger companies, I like Freescale. I see Jose here, where you really have to, the difference in 2 or 3% gross margin is a really big deal. It's basically the difference of keeping your job or needing to look for another job. And in some markets, it's a difference between profit and loss. And you really got to milk that last thing out. You can't say, what the hell, we'll go to a 424 package, no big deal. Some of these really high-end startups, you're building a supercomputing chip, you don't care. Throw another dollar at the problem, no big deal. But, a lot of guys, the last 5 cents is really, really important. And so what we want to do is give people flexibility. If they need to look for that last little bit, they can do it, and if they don't, then they have a really simple way to solve a problem.
Any other questions? I know, your IP is in a lot of the consumer applications in gaming and mobile devices. So, I mean, you're pretty well spread out there. I mean, you're in a lot of products.
Yeah, pretty much everybody that's ever built a chip has bought something from True Circuits.
Right.
I mean, the same way with DDR. Obviously, a clock is, pivotal, right? We all build synchronous circuits, so there's a PLL in pretty much every chip that's been built in the last 10 years. So that's good. I mean, we're blessed in the fact that we have a lot of really good relationships, people that know us, people that trust us, and they believe that we'll be able to do this. And it's essentially a timing problem. So,
well, you can find all of True Circuits IP, their whole portfolio on ChipEstimate.com. Very easily. So if you want to stick around and stay and talk to Brian, we'll also show you. We'll take you over to our demo station and show you how quick it is to find all their IP on the in the True Circuits catalog on ChipEstimate.com.